This is the walkthrough video for PCTC 2021-2022 round 2 question 12 alphabet caves. Okay, so question 12, what does it want from us? So we're given this cave system and we want to get from the start to the finish, the first character to the last character, the first cave to the last character, the last cave. And then we're given a number. And the idea is that we want to, if we were to find all possible parts of this cave system from left to right and sort them alphabetically, the number that we're inputting is the number where the desired path is if you were to sort these possible paths alphabetically. I mean, the example kind of shows you what you're meant to be doing. And this question is question 12. So it's going to be difficult. And crucially, what makes it so difficult? Well, if you look at the constraints, we see that the first input string will be a maximum of 52 characters. That doesn't seem too bad to me. Like 52 characters, that's not that big of a cave system, right? And I mean, I can already kind of think of possible methods to solve this problem. But then it says n will satisfy, it's bigger than 1, of course, but it can also go up to 4 times 10 to the 10. That's a huge number. So n can be a huge number. And so whilst this 52 didn't mean anything to me, this tells me that there are going to be like billions of paths, more than billion, billions of paths that we kind of have to look through. And that is a huge number. And that's what suggests to me that we need to write efficient code. And the question basically tells us that is the crux of the problem, because it says here, programs must complete in under 3 seconds. That's basically just telling us that our code needs to be efficient or we're not going to get 10 out of 10. Now, I actually remember solving this, or doing this problem 3 or 4 years ago when I did PCTC in my final year. And this was the problem. This was one of the questions that I was given in my team. And I actually struggled. I could only get, I think it was 6 out of 10 in it, maybe even 4 out of 10, probably 6 out of 10, or maybe 7. And that's just because I couldn't get my code efficient enough. Now, from memory, I think there are a couple different methods you could have used to solve this. The first one is, I'm pretty sure it's just a standard breadth first search, or maybe a depth first search, one of those two. But if you code it in a certain way, you can just about get it efficient enough to score all 10. I think that's a bit of a scummy way to do it. But yeah, if you code it in a very, very, very specific way, then you can get 10 out of 10. I'm not going to cover that because, again, I think that's scummy. And honestly, that's probably a problem that the creators of this realize and will ensure is not a problem ever again. So yeah. Now, the second way you can solve this is by taking a purely mathematical approach. And the third way is the way we're going to do is dynamic programming. Now, the foundation of the dynamic programming approach we're going to use is very similar to the mathematical approach, except that we're not going to go into that much maths. We're going to try and logic through it a little, as opposed to just do a ton of maths. But we should kind of, at a high level, understand how the maths method works. So essentially, the default method, and the method you can kind of see in the example, is that they compute every single possible path from the start to the finish. So they compute every path from A to F, in this case. And then they sort that list. So they have a list of paths, and they sort the list, and then they select the nth path. So the 6th path, in this case, that's that one. And that's going to be very inefficient when it comes to huge numbers, right? Because firstly, if you were to sort a list of like 40 billion numbers, well, that's gonna take forever. Like if you were to run that code, you are just going to click run and sit there in front of your computer watching your code just run for a while. So we don't want to sort things. Now, I believe you might be able to come up with a method that involves generating all of these without having to sort them. And that would certainly be a good method. I think that'll probably be enough that'll probably be efficient enough to get you 10 out of 10. We're not going to cover that because, again, I think that's a nicer approach to that. But ultimately, what these approaches all have in common is that you pre-compute every single path until you get to your final answer. What we're going to do is we're not going to compute any other paths. We're going to take our final answer. So in this case, we want the 6th path, and we're going to construct our final answer, A, C, D, E, F, from our input, and we're only going to construct that specific path. We're not going to construct every other path. We're going to only design our algorithm so that it only ever creates and searches for the one path that we want, the answer path. And that way we kind of reduce the time. That kind of makes sense, right? Because instead of having to create all of these billions of paths, we're creating the one path that we want. And we need to find a way to do this. because if you do find a way to do this, then it's probably going to be way more efficient, or at least efficient enough to run in under 3 seconds. Okay, so the reason that this mathematical approach works is this is alphabetical, right? And so you can say at a certain point in time, roughly where your answer will lie. For example, if you look at these, all of the answers that start with, so all of these obviously start with A, but all of the answers that start with AB, all the possible paths that start with AB are at the beginning, all the possible paths that start with AC are at the end. Now, all the possible paths that start with ABC are in the beginning, and then so on. ABD are next, and then ACD are next, and then ACE are next. And you can kind of see where I'm going with this, which is that you can figure out how many paths there are for every letter that you wish to use, right? So we can figure out that there are 8 paths in total. Then we can figure out that, for example, 5 of them start with AB, and then we can figure out that 3 of them start with ABC, and so on. And we can figure out how many paths start with these certain letters, and we can slowly build up our letters using that maths to eventually come across or finish and reach F, and then print off our final answer. Now, if you were to do the maths approach, I think there would be a lot of extra maths that you'd have to do this. So the place where the maths comes into this problem is essentially figuring out how many possible paths do I have left remaining given my starting letters. So if I were to start with AB, how many possible paths exist? In this case, 5. And to figure out the maths of that it's not super difficult. Like, I think if you are year 11, then if you kind of just sit there for a while and try to work it out, you will be able to eventually. But it's definitely not easy. It's definitely not easy. And personally, I prefer the dynamic programming approach, which is the approach that we will use because using very little maths and mostly just logic, we can construct those numbers and then use those numbers to construct our final path. Okay, so let's try and draw this. So A, B, C, D, and F, this is our cave system. And oops, let's just refresh that. It's lacking a little. So this is our cave system. And you can kind of imagine these turquoise squares rectangles. They're all, they all represent one cave. And so, for example, the first rectangle represents A, the second rectangle represents B, and so on. And in fact, to kind of make that more obvious, I'm going to write the letter directly above the cave that is represented, that represents the letter. Okay, so what am I going to do? So with dynamic programming, you pretty much always have a goal. And so in this case, we're talking about one-dimensional dynamic programming. We won't bother talking about two-dimensional, they're much harder. With 1D dynamic programming, our goal is to essentially create a list that stores useful information for us. And as we kind of discussed earlier, the useful information that we want to store is how many possible paths do I have left remaining given a certain starting string or given a certain starting path. So we could kind of want to create a list that solves that problem. And the way to solve dynamic programming puzzles is typically you start at one end and then you work your way through to the other end. And you use all of the information that you've just calculated to figure out the next one. And so you basically continue to build off everything you've currently got to figure out the next one, and you keep doing that until you've reached the other side of your list. So in this case, I'm going to start on the right-hand side. And that kind of makes sense, right? Because our goal is to get to F. And so we can say, well, how many possible ways are there? So if we were to start at F, how many possible ways are there to get to F? And I guess you could say there are 0 or 1. In this case, the answer is going to be 1, and I'll kind of make it clearer why. And that's because if I were to give you a starting path of F, how many possible paths are there to get from this to your final answer? Well, this is a final answer, and there is one of them. There is one possible correct answer to go from F to F. Or like, imagine, for example, and I think the input says that you might actually just get an input string that is only one character long. So if your input string is A, right, if that is your cave system, then there's only one possible way to get from A to A. And then the answer that's going to be printed out is just always going to be A. So yeah, that's why we have a 1 in this box, because we're saying if you start at F, how many possible paths are there? Well, there's 1. Okay, now if you start at E, how many possible paths are there? well, there's also 1, right? Because from E, the only place you can go is right. You can only move right through the cave. It's a one-way system, the question told us. And so, like, the only possible way is to go from E to F. Now, this is where it gets interesting. If I'm at D, how many possible ways are there to get from D to F? Well, if I'm at D, I can either jump 1 or go through 1 cave, or I can go through 2 caves. So if I go through 2 caves, I'm automatically at F already. So there's one way to do that, which is DF. Now, if I jump 1 cave, then I have DE, and now that I have DE, how many possible ways are there to get from DE to DEF? Well, there's only 1, right? You just jump 1. And so our 2 possible routes are, let's draw that better, that and that. So these 2 are our final strings in this case. So there are 2 possible routes from D to F. And we'll do one final one, which is C. So if our input string, if the start of our path was C and we want to get to F, what do we do? Well, we have 2 options at pretty much every cave. We can either go to the next cave, or we can go to the next cave. Those are the only 2 things we can do at any given cave. So if we go to the next cave, we're then at D. And how many possible ways are there to get from D to F? So if we have a string of CD, how many possible ways are there to get from CD to F? Well, there are 2, right? You can either do CDEF or CDF. So there are 2 ways if you do one jump. Now, if you do a double jump from C to E, how many possible ways are there from C to E to get to F? Well, 1, right? You can only move 1 more cave to get to F. So there's only 1 possible way. And so in total, if you were at C, there's going to be 2 plus 1 possible ways to get from C to F. There are 3 possible paths from C to F, given you are at C and you want to get to F. Now at this point, you might kind of begin to see some sort of pattern, which is that the number that we just wrote, 3, that was the addition of 2 and 1. And that kind of makes sense, right? Because at this given cave, C, you can only do 2 things. You can either go to D or you can go to E. And if your goal is to, in this box, write how many possible paths there are from C to F, well, to do that, you kind of have to look at all the potential next steps you can take and sum all of them together. So if I were to take a step to D, well, there are 2 potential paths there. And if I were to take a step to E, well, there's 1 potential path there. And so my final answer in this C box is going to be 3. And that might be some that's like kind of one of the groundbreaking pieces of logic in this problem. And so if you don't get that, just pause the video here, try and play around with these numbers. But I'll finish off the rest of this table or this list now. So B, well, that's just going to be the next 2 added together, because you can either, from B, you can either go to C or you can go to D. And so we have to add the 3 and the 2 together to get 5. And let's just go back to purple. And then we can once again apply the exact same logic to A. If we were at A, how many possible ways are there from A to F? Well, from A, you can either go to B or you can go to C. And then from B, there are 5 ways. From C, there are 3 ways. And therefore from A, there are 5 plus 3 ways, which is 8. Now, this is just an example, so we could easily calculate that by hand. And, if I didn't kind of describe every part of the process, you can do this in like 10 seconds. This is just adding single-digit numbers. This is easy. The logic is the hard bit. But obviously, this is programming. We kind of have to figure out a way to generalize this, a way to get the computer to generate these numbers, especially when our list is, for example, 52 characters long. I don't really want to have to spend 10 minutes in PCTC calculating a 52 character long table. And yeah, the algorithm here is relatively simple, because as we'd said, all you need to do is you need to add the next 2 numbers together, and that's going to be your current cell. Like this cell was the next 2 added together, and so on. Now we have to start somewhere, right? And we have to manually add E and F. And that makes sense, right? If I'm at E, I can't say to Python, add the next 2 numbers. Like, there are no next 2 numbers. There's F and there's nothing after F. And so we can't just apply our add the next 2 numbers idea to this. And so we have to manually add the 1 to the E and the 1 to the F. And that's nice and easy, right? Those are like our base cases, essentially. Those are the cases that we can calculate by hand. They're very easy to do. And then once we calculate those 2 by hand, and well, we're not even calculating anything, right? It's just 1. So once we figure them out by hand, we're just going to insert them into the list in Python. And once we've inserted these two, we can then apply our algorithm to the rest of the list, because that will now work. Because, for example, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on. And we can build up the rest of the list like that. Okay, and one thing I will say is at this point we can kind of do a sanity check to make sure that what we're doing seems valid. So we can look at the first cell, that's SA, and we've got an 8 written in there. That tells us there are 8 possible paths from A to F. Is that right? Well, fortunately, because we use the example input as our example up here, we can go back to the question and can count how many of these are there. And there are 8, right? So these are the 8 possible paths from A to F, and our list up here correctly predicted that there are going to be 8 possible paths from A to F. And this is the bit where we kind of do the maths. This is the bit where we create a useful list, the list that kind of gives us the insight into the rest of the problem, that kind of pre-computes stuff for us, because it pre-computes how many possible paths there are from every given letter. And that's going to be incredibly useful later on. But yeah, before we get into the real meat of the algorithm, this was really just a precursor to the algorithm. I know it's difficult, but this is just a precursor. Let's code this all up. So the first thing to do, as always, is to take in our inputs. And so we're going to have caves is equal to the first input, and then the next input is going to be the target, let's call it. That's going to be an integer. Now we want to build up this list. So I'm going to call this list DP for dynamic programming. And initially, to begin with, let's just kind of create this empty list. Not empty, but we want a list of all of these caves, right? Like if you imagine 5-10 minutes ago, I started off with a row of 6 caves. And so I'm going to say each cave just starts off at 0, whatever. And how many caves are there? Well, that's just going to be len caves. And this is a construct in Python that is quite useful. I'm not sure if you come across it, but for example, if caves was our example input up here, len caves is 6, and therefore this is the list times by 6. And what that means is you're going to have 6 zeros like that. And so that's 7, I think. Yeah. And so line 4 is just a really efficient way of kind of creating this list of the correct number of zeros, and each 0 represents a cave. Awesome. Now let's build up this list. But before we do that, remember, we have to add our base case, the 2 1s. So let's say the very last number in DP is going to be a 1, and the second last number is also going to be a 1. That's the E and F in this example. Now we can write our for loop to build up the rest of the list from right to left. Let's do for cave in range. And what's our starting position? Well, we're going to count in the minuses, right? So we're going to say that we want to count from 1 to 3, so that's -3. What number do we want to go up to? We want to go up until minus len list. So that's going to be minus len caves. But remember that Python always stops at one thing before the ending thing in your range, and so you have to go. We always have to go one step further than we actually want in our range statement. And so we're gonna take away another one to go one step further, because Python will stop at one step before that. And what's our increment? Well, we're going downwards, right? We're going from -3 to -5 in this case. No, -6. So D is -3 and A is -6, and we're going from -3 to -6. So our increment, or our change in every step, is -1. We're going backwards. Okay, and then what are we doing? Well, we're changing DP cave to be equal to DP cave +1 plus DP cave +2. So we're just adding the next 2 caves, the values of the next 2 caves to our current cave, and adding that in the list. And just to confirm that seems to work, let's print DP, and let's use it, run it with our example A, B, C, D, E, F, and we're expecting 853211 to be printed out. And yep, 853211. So our list is correctly being built in Python. Lovely. We now have our dynamic programming list. So now let's get into the meat of the problem. So we have this list. Now the question is, using this list, how do we generate the one path that we want? Well, let's first draw a number line. And in this example, there are 8 possible paths, as we already said, and as the question tells us, there are 8 possible paths. So if you go to our number line, let's say the left of the number line represents path 1, and the right of the number line represents path 8. And in the example input, we want path 6. And so 6 is going to be like roughly there. Let's do it in a different color. So our aim is where the arrow is, because that's where 6 is. So so you can kind of imagine or visualize this in the sense that we have 8 possible paths across this entire number line, and our job is to figure out at what point in this number line do we find no. So we're already given a point in this number line, which is 6 in this case. And our question is to find, our task is to find the path that is at that point in the number line. So we kind of almost want to narrow down this number line until we essentially narrow it down all the way to 6. And once we reach 6, that is when we've built up our path. So we obviously start with A, right? Like we start on the left, that's the whole puzzle. We start on the left, and so our string starts off as A. And now we have a choice. We can either go to B or we can go to C. What do we do? Well, B has a 5, C has a 3. What do those numbers actually mean? Right? We know they mean how many possible paths there are from B to F and C to F respectively. But what do they actually mean? What do these numbers actually indicate? Well, if you think about it, if we were to choose B, our list is now going to be AB. Sorry, our path's now going to be AB. If we were to choose C, our path is AC. AB comes before AC in the alphabet. And we see here, all the paths starting with AB come before all the paths starting with AC. And how many are there? Well, there are 5 starting with AB and 3 starting with AC. Those are the same 2 numbers we have in our dynamic programming list up here. So we can kind of visualize this on a number line, right? We can say that if this is 0.5, it's probably a bit further wrong. If that's 0.5, and 6 is probably a bit further wrong, but oh well. If that's 0.5, then AB is represented by that, and AC is represented by that. Right? At this point, the first 5 paths in our possible paths all start with AB. The next 3 all start with AC, and this is our number line. And we want to reach 6. So what do? We obviously want to go to AC, right? Because 6 is in the region of AC. 6 is in the second part of a number line. And so in this case, we want to go to AC. So we jump to AC. But alternatively, say our goal was 3. If our goal was 3, then that's going to be somewhere here. And so we'd obviously want to jump to AB, because 3 lies in AB. And then we essentially want to keep applying this algorithm. We want to keep jumping into the correct part of the number line until we reach our final answer. So going back to the going back to the target of 6 example, we've jumped to AC. Now from AC, we can either go to D or E. Well, if we were to go to D, D covers the next 2 paths. Let's make that more representative. D covers the next 2 paths, and E covers the next 1 path. So that is going to be ACD, and that's going to be ACE. And what are these numbers actually? So the number that separates them is a 7. So that's a 0.7, right? Because from 0.5, the next 2 paths start off with AD, and then the 1 path after that starts off with ACE, sorry. And we can go back to our example again and see that in action. If we were to choose the AC paths, you can see that the first 2 of these AC paths also have a D, whereas the third and final one of these AC paths doesn't have a D. And we can continue to narrow this down further. Let's probably shift all of this downwards so we have enough space. And the top of the E has been lost. Okay, so we've moved from AC. Now we clearly want to go to D in this case, because that's where our 6 lies. So we want to go to D. Now at D, we have 2 choices yet again. We can either go to E or we can go to F. What do we want? Well, let's draw that on the number line. Again, let's kind of shift stuff down so we have more space. So if we were to go to E, we get the first, so yeah, just to clarify, our number line is currently realistically only this part of the number line. Like we are only in that region of the number line. We started off with the massive green one, then we narrowed it down to this green one I've just drawn, and now we've narrowed it down further to this top green one. Now we want to narrow it down further and further and further. We want to keep narrowing down this number line until we get to our desired number. And this is the point in which we can do that. Because if you go to E, we then get the first number. If you go to F, you get the second number. And so that would be A, C, D, E, and that would be A, C, D, F. And if we add numbers to this number line, this is going to be 5. This is going to be the 7 from down there. And then the midway point is going to be a 6 because we're told that one of the numbers starts with an E and one of the paths has an E, whereas the other path has an F next. And so we know that this is going to be 5, 6, and 7. And, well, we want path 6. Now the question is, which of these is path 6, right? Because on our number line, we haven't actually chosen a path to be assigned to a number. And essentially, the number that we want is going to be the smaller one. So we want the smaller path. We want to take that path. And the reason is because we are still building up our path list, right? And essentially, what we're doing is we are currently at path 5. The way to think about this is we are currently at, let's choose another color. We are currently at whatever the smaller point on a number line is. So we started off at path 1. Now we've eradicated everything up until 5, and then we start off at path 5. And we're now at path 5. And do we either want to choose the current one or the next one? And we want to choose. So when I say we're at path 5, we're not actually at path 5. Like we've already discarded path 5. As in, like, remember, if we were to go to B, we would actually be at path 5, but because we went to C initially, and we discarded path 5. So we're not at path 5. We're like just after path 5. I guess. Yeah, you can kind of say, yeah. So like, if we were to continue going as slowly as possible, essentially, we would make path 6. That probably wasn't a very good explanation of why we're choosing the smaller one. I'm struggling to explain that well, to be honest. I haven't thought about this beforehand. So yeah, pause the video now if you don't understand that bit. But essentially, we're going to take the smaller one of these numbers because taking this one represents path 7, taking this one represents path 6. And if we were to take that left one, then we can add the F to make the final step, and that would be our answer, A, C, D, E, F. Is that right? Absolutely, that's what the example output had, A, C, D, E, F. And that's the list, that's the path that we managed to build up. And so our algorithm, or our idea here, seems to work. And now we just need to figure out how to generalize this into Python code that will work every single time, no matter how long our list, our cave system is, and how long our list is, and whatever our target is. Now, what was the condition for jumping, for deciding when to jump to the first one or to the second one? Well, if our target, which was, for example, a 6 down here, if our target is greater than the number in B, we wanted to jump to C. Whereas if our target is, let's draw purple. If our target is 3, well, we want to jump to B. So if our target is smaller than the next number, we want to jump to that next number because that next number encapsulates our target path. But if it's not, then we want to jump to the next number. So let's write the code to do that. And so our starting path, which we're going to slowly build up over time, just as we were doing with the red things, the red strings here. So our answer is going to be starting off with A. Our current position is going to be 0 because we're currently at A. So we're currently at the left part of the list. We're currently at DP0. And now we're going to have an infinite while loop. We're going to change this while loop so it's not infinite later on, but that's going to be a bit harder. So we'll deal with that later. So at every step in our algorithm, what do we want to do? We want to look at the next number. And as we said, we want to check if the next number is bigger or smaller than our target. So we're going to say, if the next number, which is dp pos plus 1, if that is greater than or equal to our target, then that's where we want to move. So we can increase pos by 1. If that isn't where we want to move, then it's a bit more difficult. So if that isn't where we want to move, then of course we want to increase pos by 2 because that's the only other place we can move. But now what do we want to do? You might notice an issue, which is that if our goal is, for example, 6 and we move to C, like 6 is never represented here. 6 is not represented here. And that's because if you recall back to earlier, we've fundamentally changed our number line. Our number line is gone from this massive green one to this smaller green one. When we made the decision to move to C, our number line changed. And if our number line changes, we should also change our target. So this 6 should actually have been changed to a 1 because a 2. Because relative to our new number line, we now want path number 2, where this is path number 1, and our number line ended at path number 3. Not 3. I think that would be 4. Not 4. Yeah, 3. Yeah, so whenever we jump 2, we want to change the size of our number line, which we've already established. But when we change the size of our number line, we need to change all of the numbers on it as well, right? Because our DP list up here is not relative to the entire thing. It's relative to what? It's relative to everything that we're considering at that moment in time. We have to consider the context of where we are, and that therefore means that we have to change our target respectively so that we ensure that our target is always within the constraints of our new number line. And that makes sense, right? We built up this DP list from right to left. We built it up from small to big. And so we can't come in with a big number like 6 and keep that number throughout our algorithm and expect to find the 6th path. Because by moving to C, we have completely moved away from any possibility of getting paths 1 to 5, right? Paths 1 to 5 all start with B. Therefore, if we then go with a C, well then we've completely gotten rid of all the possible paths that start with a B, which is the first 5 paths. And so we can kind of just ignore that. We can now normalize our target from B to C. And that's going to be from 6 to, actually, I think I was wrong here when I said 2. In this case, it would not be 2. We'd want it to be 1. So in this case, our target is going to be 1 on this number line. So I guess the best way to communicate that would be to change that to a 0. Say our target is 1, and this number line goes up to 3. Like that. It's a bit confusing. Yeah. So that is essentially our new normalized target. And the way to essentially communicate that to Python is by changing your target. And what are we changing it to? Well, we always have to decrease it because we kind of eradicated potential options. And we're decreasing it by the cave that we skipped. The cave that we skipped is essentially the cave that's right before our brand new position, so plus minus 1. So when we skip from A to C, we skipped B, and therefore we're taking our number, for example, 6, our target of 6, and we're taking 5 away from it to get a brand new target of 1. And then that's our brand new target, which is in line with our brand new number line. And we want to do that every time, and that does make sense, right? If we're to go once again back to this, once we skip to C, then we're only looking at these 3 potential possible paths. And if you want path number 6, well, that's A, C, D, E, F, A, C, D, E, F. So path number 6 is the first path that starts with AC. And so that makes sense, right? In this case, we're normalizing, we're changing our target from a 6 to a 1. And that makes sense because we see here that path number 1 of this chunk of paths is the answer. So once we change our scope, once we change the range of the path that we're looking at, we also need to change our target. And this is pretty much all of our code, right? Now we can kind of just end the code by printing off answer. But remember, we need to go back to line 14 and make sure this while loop is not actually infinite. How do we do that? Well, when do we want to end our code? We want to end our code when we've reached F. And so there are multiple ways to check this, I guess. But the way I'm going to use this just by saying if the position is the same as the last position in the list, which is going to be len dp minus 1. If our position if our index / position is the very last one, which is F in this case, for example, then yeah, we want to end there. Because this is the while loop, we need to say, while this is not true. So whilst this is not equal to the last position, whilst we are not at F, keep doing this until we get to F, and then print off the answer. And we can submit that code. But if you were keen-eyed, you may have noticed an issue right from the beginning. Actually, no score. We should probably first fix the fact that we have no score. And, oh yes, we have no score because we're not actually building our answer list. So, answer string. So let's actually just build our answer string by, once we've made our move to our answer string, we want to add the correct letter relating to that move. So that's going to be caves pos. Now this should actually give us the points. Because now we're actually adding the cave to our answer string. But yeah, this it's not going to give us all 10 points, I think. Yeah, it gives us 9. So we're so close. What's the issue? If you're keen-eyed, you'd have noticed that we manually set E and F to 1. We manually set the last two numbers to a 1. But what if they only entered one number? What if this is the input? Then our code is going to like cause issues. There's going to have a runtime error, right? Because we're referencing the penultimate element in this list when it doesn't exist. So our list is only going to be one element long. And that's why there's a runtime error on test case 5. It's a runtime error specifically. It's not a timeout error. So our code isn't being too inefficient. Our code just is breaking. And if we look at when I've just run this example input, it says that yes, list assignment index is out of range on line 7, where we reference this. And so we need to add the edge case, which is that if len caves is equal to 1, so if there's only one cave, then, well, the answer we want to print off is really just A, or I guess caves. But both would work. And if that isn't the case, then we want to apply the rest of the algorithm that we've written. And so if we were to run that code, for example, you can now see it prints off the correct answer of A. Like there's only one possible path from A to A, and that's going to be A. And so if we submit this code, we should now get that final test case 5, and yeah, we get 10 out of 10. So this problem, very difficult, very algorithmically difficult. So yeah, pause the video. Well, I guess too late for that. But like, end the video now. Go copy this code from GitHub. Write the code yourself. Kind of try and understand every step of the process. Print stuff off as you're writing the code to kind of understand what each of these variables mean and what they represent. And run through more test cases. So in this case, I only ran through the example input they gave us to demonstrate all of these points. But if you're still confused, run through more test cases. What if it was A, B, C, D? What if it was A, B, C, D, E, F, G, H? Or, for example, run through all of these different cases until you understand why this works. And in particular, I think the conceptually hardest bit of this is probably line 22, when we have to change target. And you can probably tell because I struggled to explain that. I tried to draw pictures to explain it, but if the pictures didn't really vibe with you, then yeah, try and experiment with this yourself, because ultimately, for you to build the best intuition yourself, you're going to need to play around with the code yourself and the maths, and you're going to have to struggle to actually understand this. But yeah, I love this problem. It's so much fun, and it's of course the hardest one. I think this is the hardest one that there's been since this year actually. But yeah, hopefully you enjoyed. But that rounds off this year's series of PCTC, and good luck if you're taking it this year.